Hello, welcome to session number 12 in the series Digital Circuit Design using VHDL. My name is Anurag Nigam and we are looking into, learning VHDL for digital circuit design. And the topic for this session is going to be sequential statements. And the reason I have kept this out from the earlier sessions was that in synthesis, okay, you are allowed to use the sequential statements, but then you are not sure of the optimized synthesis. So basically, you have left it to the synthesis tool to do the optimization, and this is something which I don't personally prefer to leave to a synthesis tool, the implementation part. So that's why I have been covering up till now either the data flow style or the structural style. But now I'm going to talk about the sequential statements. And in VHDL, its roots are in a language called Ada. And Ada is inherently a concurrent language. So that's why VHDL is a concurrent language. And sequential statements are in some sense foreign to VHDL. And that's why they are packed into another concurrent statement known as process statement. So process statement in its own is concurrent, but then the statement it houses inside its body, they are all sequential, other than the simple assignment statement. Now sometimes in some examples in Douglas Perry, okay, there are statements which are conditional or selected assignment and they are included inside the process. Well, that is not allowed. So that's a problem with the book there, which has to be corrected, right? Only statements which are allowed inside the process, which is going to be a signal assignment, is going to be a simple assignment. It cannot be a conditional assignment or a selected assignment. So process block on its own is concurrent. It houses all the sequential statements other than the selected and conditional assignments. Simple assignments are allowed, nothing else than that. Okay, so having said that, okay, we are going to explore a process statement. Okay, and then what are the sequential statements go inside the process statement. So let's list them down. Okay, so first is going to be a for loop. Okay, for a condition, then you say loop, sorry, and at the end you are looping a set of statements, and at the end you are going to say and loop. Now, unlike the for generate statement, which requires a labeling, okay, labeling is a must in a for generate statement. Here the labeling is not a must, right? But sometimes labeling can help. For example, if you want to exit from a loop, right, you can use exit and then a label. So basically you can exit from not only the innermost loop, but you can exit from the outermost loop also if you have a label, right? So label in case of looping has one advantage, is that you can loop out. Okay, you can break out of the loop using exit statement, right? And then you can label it which for loop or which while loop you want to exit, right? So looping or iteration, right, is the first thing which I'm going to cover. So in this case, for loop is the statement. Then there is another form of looping which is going to be while. Okay, I try to keep this small. Okay, so in while statement you have a while and then you have a condition, and after that you are going to have a bunch of statement, and so you are going to say loop, and then you're going to have bunch of statements and you're going to say and loop. Okay, so that's a while loop. Then there is branching, right? So in branching there is a, so before I go to branching, one more thing. If you want to exit the loop, okay, there is a statement called exit. Now this exit will place you one statement after the termination of a loop, right? After the end loop, whichever is the subsequent statement is going to place the execution there, right? So that's what exit does. Then there's something called next. Okay, so is exit is like break in C. Okay, and next is like continue in C. So next we'll skip all the lines, sequential statements in the loop, and then jump to the top of the loop, right? So that's what next is going to do, right? Now one more thing I want to tell you, in for loop you have an iterator which is well defined, while in while loop you have a condition which is going to terminate the loop. So while some condition is true, you are going to loop, and then if the condition turns false, you are going to exit the loop, and that condition has to be altered inside the body of the for loop. If you do not do that, then you may go into a never ending loop, right, which you have to avoid. Okay, so now this is there. Then sorry about that. Then the other statements are if a condition, then a bunch of statements, okay, and then there is an optional else if, okay, another condition, okay, then another set of statements. So these are optionals. So let me turn them gray. Okay, and then you are going to be back to the last one, which is else. Okay, and else a bunch of statements, and then you say and if. Okay, let me tell you one more thing about this. Okay, in case you exit, then if statement is valid, like you don't need a next, you don't need a else. But if you don't perform an exit, you have to have a else, right? And the else is basically like others, like in a selected or in the selected assignment you have others, right? So all other conditions. So that's why there is else. Okay, else doesn't pair up with the else if, it pairs up with the outermost if, right? And else if, okay, is optional, right? You can have as many else if as you like. Now if you enter a if statement, okay, then one after the other the conditions are checked. Whenever you meet a true condition, okay, whenever you meet a condition, okay, then the entire if loop is exited. So only one out of the many branches is going to execute. Now like this there is a case statement. Case, so let me just put it back. Case, come on. Okay, case, a condition is, okay, and then you have a when, and then you have that condition there, and then you are going to say this, and then your bunch of statements, and then you're going to say, okay, when again. So you can have as many when as you like. When a condition, okay, when a condition, then you're going to do again something, and so on. And then last thing which you're going to see is when others, and then you have this condition and then a bunch of statements, and then you can say end case. Okay, so this is a case statement, right? Let me see if I'm recording. Yeah, so that's a case statement. Now the next thing is going to be, okay, if, for, while, case. So these are done. Now the next thing is going to be what is called a assert. Okay, an assert is used for assertion based testing. So unlike if condition is true, do something. If, okay, condition is false, don't do anything. But if the condition so if the condition turns, if the condition is true, don't do anything. If the condition turns false, then report something, right? So if you say assert a condition, and unlike all other statements where the condition has to be true, here the condition has to be false. Okay, like for example in if statement, in while statement, or in case statement, the condition has to be true for certain thing to happen. But in assert statement, the condition has to be false for something to happen. And if it turns false, you report. And you report a string. So string is something which you can enter here. And then you say severity. Okay. And after the severity, there are, some keywords like, warning. Warning means that the execution will continue. Okay. The run will not stop. Okay. That's a warning. But if you do error, the execution will stop there itself. Okay. So this is a assert statement, and assertion based testing is altogether a different area. Now I have kept these aside till now because I am not going to do synthesis using any of these statements or a process block. Okay, that's why I've kept it aside. Another thing I'll tell you, a general structure of a process statement is process, and then there is a sensitivity list. So you know that every assignment has a sensitivity list, which is the signals to the right hand side of the assignment, right? So every assignment has a sensitivity list. So all concurrent statements are basically some form of assignment, simple assignment, conditional assignment, or selected assignment, right? So in case of process, it's also a concurrent block, so it has to have a sensitivity list. So the declaration goes, or the definition goes like this: you say process, and then there is going to be a list of signals here. These are the signals which are in the sensitivity list of the process. So any change on those signals or any events on those signals, okay, process block is going to execute. And what is a process block? It is a concurrent statement which doesn't execute completely, it just goes on a hold. Okay, so basically you spawn a thread like a process, okay, and that basically comes to a hold, and it is on a hold till something happens to the signals in the sensitivity list. Okay, something happens, like some event takes place on the signals in the sensitivity list, or they change, like they change, right? Then the process block executes all over again. So any change in the signal in the sensitivity list, it is going to execute the entire process block, which means all the statements inside the process block. So a process block is like a process which is on hold, and it is not terminated. It is on a hold, okay, as long as you don't exit the simulation. Okay, it is on hold, and it is going to wait for a certain condition, okay, which may be an event on a signal. But this is the general form. Then what you can have here, after the sensitivity list, you have a region which will be called the I will put it in a different line. Okay, so there will be this region which will be called the declaration section, and then you are going to have a begin, and then you are going to have a bunch of sequential statements here, right? And then you are going to say end process. Okay, so this is how you do the this is how you do the process block. And what are the applications? Of course, the process block I'm not going to use in a synthesis. Okay, this is usually used in basically simulation, right? Right. So it is used on a simulation where you have to generate a set of signals, or this is like a generator in any other language, right? Okay, so if you understand what is a generator, okay, so in my other series you will know in other languages there's something called generator. So what it means is that this process is on a hold, okay, and whenever it is triggered, it's going to start all over again and then come to hold again. So that's a process block, right? So here in this declaration section, you can have variable assignments, you can have type declaration, you can have a function declaration, you can have a procedure declaration, but you cannot have a signal declaration here because signals are foreign to a process. Now the difference between signal and variable I have already explained. Variable is a wire, it's equivalent to a wire, right? While sorry, a signal is equivalent to a wire, right? While a variable is a stored location, it's a memory location. Signals have drivers. Variables do not have drivers. Signals are going to be assigned at a delta delay or at a certain specified delay, right? Okay, which may be inertial delay or a transport delay, while variables do not have delay. Okay, as soon as the expression on right hand side is evaluated, the value is assigned. So basically they don't have a sensitivity list, they only have expressions. Okay, just like expressions in C. Now, according to me, okay, there is this big debate, Verilog versus VHDL. Okay, those who come from processor background, those who come from testing background, they are more close to C, right? They are used to writing programs which are one statement by one statement execution. They are sequential because processor is itself sequential, right? So that's why C language is familiar to them. Now, Verilog is is kind of a derivation of C. So inherently Verilog is sequential. But then you have got parallel constructs in it, like a always block or something like that, right? So these parallel constructs are making it suitable for hardware design. Okay, otherwise this is more like a programming language. Okay, Verilog, it is hardware or combinational circuits comes in only because of these parallel blocks. So basically concurrency is a foreign concept to Verilog. Okay, so if I was a testing guy, so if I was a testing guy, I would be more close to Verilog, right? Because that is sequential. If I am a synthesis guy, then I should be more close to VHDL. Now it's not that one language can do the testing but not synthesis, or one language can do synthesis but not testing. Both can do both, but it's just that inherently Verilog looks like sequential because it is coming from something like C, and it's like more close to people who are writing programs or software engineers or people who are into testing or verification, while VHDL is close to the guys who are doing designing, right? And if you mix the two, then you have a very complex engineer, difficult to handle, because he's thinking that everything is like, if you design a counter, you will say count equal to count plus 1. Okay, so then he would be like more like a Verilog or a testing guy. But if you ask for a designer, then he will be more like a VHDL guy. Like he would put in a flip flops, T flip flops, he would put, or JK flip flops, and then he would put a structural design to a counter rather than saying count equal to count plus 1. Though both of them are going to work, but then one of them can be optimized by the designer, other is left to the synthesis tool to optimize. So that's the difference between the two approaches. If you are a designer, I think you will be more comfortable with VHDL, and if you are a testing guy, you write test benches, then you are going to be more close to Verilog. And you can use each language for everything else. Now I'll tell you one more thing. When it comes to testing, okay, there are a number of times you have to insert delays and things like that. So there used to be something called a standard delay, or SDF, a standard delay format, which was foreign to VHDL, but then it was revised to include this also SDF, right? So now it is equivalent to you can have a SDF here, where you can take a hardware and kind of approximate delays for timing analysis, right, using SDF. Okay, so all this analysis part goes into Verilog stuff, but then VHDL, nothing stops VHDL to do the same thing. Okay, so now having said that, okay, one more thing I would tell you is, it's not that always process has to have a sensitivity list. Process can go just like that, and then it can have the remaining parts. Okay, and then you have an end process. Okay. Now what's the difference here? The difference here is, okay, I'll tell you what's the difference. The difference here is, somewhere this process has to be halted, or it has to wait. Like in case of sensitivity list, it was waiting on the event on the sensitivity list signals, right? But here you can insert your own. We can say wait on, okay, and you can wait on the same sensitivity list here. So inside, at the end of everything, you can put in a sensitivity list using wait statement. And wait has various flavors. Wait on argument or a sensitivity list. That's one way. Other way is wait for let's say 10 nanoseconds. Okay, so basically this is like telling the process block that you wait for a fixed amount of time and then you execute again. Okay, so that's like polling, right? Wait and then do again, wait and then do again. Then you can say wait for. Okay, so here wait for certain expression, okay, to turn true. So when the expression turns true, it's going to execute again. Okay, and then somewhere the expression will turn false. Okay, and then when it is again going to wait for the expression to turn true. Okay, so this is kind of complementary to polling. Polling is where the master polls something. Okay, while here it's a different form of polling where slave says that, okay, I have a flag and then I need to do something. Okay, again I have a flag, I need to do something, right? So basically the roles are reversed. In case of polling, a master is polling a slave, while in case of this kind of polling, it is the slave which raises the flag that, oh, now that some condition is true, I need to do the entire process again, right? So somewhere that condition has to turn false, otherwise this loop will not stop anywhere. It will keep on going and going unless there is a wait condition has to come. So wait has to have a meaning here. So whatever say wait until sorry, wait for, wait on, and wait until, sorry. Okay, wait until certain condition is true, then that condition has to immediately turn false because it has to come in and halt somewhere, right? And then that condition turns true again, and then it goes over. If that condition doesn't turn false, then the process thread will keep on going and going without stop waiting anywhere, right? So these are the four variations: wait on a signal, wait for a certain time, and wait until certain expression is true. Okay, so these are all sequential statements, and this is a process block. Now, am I going to use Vivado for this? Answer is no, because Vivado is basically a synthesis tool. It basically addresses a certain subset of VHDL, which is used for synthesis. Okay, so we have been exploring a certain subset of VHDL, which is for synthesis. Now here we have to explore something which is going to be used for testing or writing test benches, or doing some kind of a assertion based testing or verification, right? Then the tool here is going to be different. Okay, so I'm not going to do this in Vivado. I'm going to do this in something called QuestaSim, and there's something called ModelSim which is the same, but QuestaSim is far more advanced in terms of testing. You are different verification methodologies can they are facilitated in this tool, right? So let's go ahead, and so basically it looks like this, and there are a bunch of libraries. IEEE is one of them, right? Standard is one of them, you can see over here. Okay, it opens the previous project, so I'm not interested in that. I am going to make a new project. File, new project, and close the current operation. Yes, so now you give a name to a project. Okay, so I am going to call this as okay, tutorial 2. Okay, tutorial 2. And project location, I have made a directory. If you want, you can make browse and make your own directory. And then default libraries work. Now let me tell you, I'm revisiting this fact. Okay, work is inherently visible to the project itself, but then the work is shared. All the projects have the common work. Then you are going to mess up, because two projects may have same entity name. and if you put it in a work, then there would be a source of confusion. So usually I don't do that, and I will put here my own library. Earlier I was calling it my circuits. I will call this one as my test. How's that? Okay, so I am going to talk about testing on this line. Okay, on the other line, which is going to be synthesis line, I'm going to be talking about IP based block synthesis. But here on this line I'm going to be talking about testing. So that's there, and remaining you can leave as is and say okay. And as soon as you finish that, it says what you want to do: create a new file, add an existing file, create simulation, or create a new folder. I'm going to say create a new file, and here file type is VHDL. You can choose any one of these, right? So there are lots of platforms for testing. Okay, Verilog, system Verilog, okay, stuff system C, okay, Vera is a platform, right? So you can do any form of verification. I'm going to use it for VHDL top level, and here I'm going to say is use process. So I am going to just naming it like that, so because I'm going to show you what is the use of this process statement. So I will say use process, say okay, and I can close that. Now this is over there with a question mark, means that it is not compiled yet, it is empty. Okay, so I can double click this, and as soon as I double click this, okay, I open this. Now I okay okay, I am going to put you on hold. I want to make this text large, so that is under preferences, so I have to search for preferences. So let me put you on hold for a second. Okay, okay, welcome back. I just adjusted the font size here so that you can see it. Okay, now unlike your tool, which was Vivado, it was writing a lot of stuff for you. Now here you are provided with a blank file, so you have to start with a library, IEEE, and then you have to say use IEEE dot std underscore logic underscore 1164 dot all, right? And that's it. So basically this is the key line which you always write. Okay, so now I have to show you a process block. So I have to first write the entity. Okay, so now the question is, what am I going to design in here? To demonstrate a branching, for example, if statement. Okay, I am going to use a process block. Okay, and I am going to design a 4:1 n bit 4:1 multiplexer, right? So I'm going to write an entity, and I'm going to say entity, the file name, so that it is easy in debugging. It's not necessary. Okay, use process is, and then you are going to say port, and then you are going to say port finishes here, and this one is going to receive I0 comma I1 comma I2 comma I3. Okay, and this is of mode in, and it is a std underscore logic underscore vector. Okay, and here I can say n minus 1 down to 0. Now here I don't have n because I don't have a generic yet, so I'll put here a generic GENER, and in that I can put here n is an integer, and it has a default value of 8. So that's done, and here I can write the other stuff. Okay, s1 comma s0 is again mode in, and it is a scalar of type std logic, right? And then finally you have got q. Okay, q is a form out, the mode is out, and it is a std underscore logic underscore vector, and it is going to be n minus 1 down to 0. That's the end of this, and the last one doesn't require a semicolon, it's after the boat. And then you can say and the name of the entity is use process. Okay, so this is how you normally write an entity. Now you are going to write an architecture. Okay, and I'm telling you, though I'm implementing a mux like this, but this is not what I like to do. Whatever previously I have taught in the previous sessions in Vivado, that's how I design components, not this way. Okay, this is mainly for testing stuff, but to demonstrate I'm just using it. Architecture UP of use process is. Okay, and then there is a declaration section of architecture, then you say begin, and then there is a body of architecture and you say and UP, and that's how you define architecture. Okay, so now inside this begin and end UP, the body of the architecture, I can only have concurrent statements. So I am going to have a process block, process with certain sensitivity list. So now let me tell you, you have to include all the signals which you are going to expect to change. If you miss out any of the signals, then there is a classic problem here. Okay, so whatever you expect to change should be put in here, so otherwise there will be some side effects. Okay, so let's put it that way. Okay, so now here it depends on I0, depends on I1, depends on I2, depends on I3, then it also depends on S1, it depends on S0. So this is the sensitivity list of process, and then you are going to say begin. So you're going to begin the process, and then you are going to say end process. Okay, so this is how you're going to write the process, and let's distinctly say what is what. This section, okay, and that's a declaration section of process, and then that's the body of the process. Okay, so now I'm going to write in here. So I can say if, right, I'm going to write a statement. If S1 is equal to, so there is no equal to, keep in mind, this is not a high level language, equal to 0, and S0 equal to 0, then, okay, so now this if need not start with capital I, but capital small. In VHDL they are case insensitive. So if this condition, then you are going to do something, then I am going to say Q is assigned. Okay, Q is assigned some value which is I0. Okay, sorry. Okay, now is this done? Well, up to this condition it's done. Then I'm going to say else. So it is not ELSE, it is ELSIF, else if. So there's going to be another condition. So this is like multiple branching. Whichever turns true, that's going to terminate the if statement. So Q will have one driver anyways. Now there is no multiple drivers, unlike selected or conditional assignment. You could put only one driver, because here Q assigned I0 is treated as a sequential statement, so it is not generating a driver. So you keep in mind that that's not what's happening. So there will be no case of a multiple drivers generated, because it's inside the if statement. Okay, if certain condition where S0 becomes 1, then do something. Q is assigned I1. Okay, then you can say else if certain condition is going to be 1 0, 1 0, then Q is assigned I2. Else if no E, it is else if certain condition both are 1, then do something. Okay, and then finally for every other case I have a else. Q is assigned, and then here I'm not sure about the size, I will say others, and this is aggregation Z. Okay, so this is how you write a if else statement, and then finally you have to say and if. So this is a complete statement, and you can save it here, and then you right click it and say compile, and says compile of use process VHD was successful, means that there are no errors. Now you can simulate this, simulate, and say start simulation, and then you have to go to my test. Okay, and this is the only entity available here. Say okay. So it's going to launch an objects window. This is going to be a VHDL object, and it will hint to a line where it has stopped. Okay, so let's see what it's going to do. Okay, so now you see here objects window, like what you see in that also in what you call Vivado also. But you see here line number 12, it has come to a halt. It says okay, simulation is at halt at line number 12 and is pointed by arrow, means it is waiting. So as I told you, process block is like a thread which has been spawned, and it's now waiting for something to happen, right? So it is waiting for something to happen to I0, I1, I2, I3, S1, S0. So that's supposed to happen. So I am going to add these. Okay, I'm going to add this to wave window. So if I right click and say add wave, and that's added to the wave window. Okay, so now I have to put in these values. So I am going to say force, and I'm going to say this is a hex which is 8-bit wide. So the convention is like 8, which is the size, then tick, and then H means it's a hex. Okay, this is a common VHDL convention, not just something to do with this tool. And here I can put here 2a, which is my favorite number, and then here I can force a constant 2b, and then here I can force a constant 2c, and then the last one I'm going to force a constant 2d. Okay, so basically I0 to I3 is 2a to 2d, and then I am going to force S1 to 0 and S2 to 0. So that's a 0-0 condition. It'll cause I0 to be passed on to Q, right? And this is for 100 nanosecond. I am going to run this. So if I look at Q gets a value of 2a, which is I0 has a value of 2a. Now if I make S0 as 1, then it will be 2b. Okay, so 1, and if I simulate this again, so it's now 2b, so that's I1. Then I can make it force a constant 1 here. Now it is going to point to I3, which is going to be 2d, right? And then I am going to make 1 0 here as the input. Then it is going to go to I2, which is going to be 2c, right? So if I run this, it's 2c. Now if I give a condition which is here x, or let's say u, let's see how it's going to behave. Okay, and say enter. So what do you see here? You see here Q has a value of Z, which means that for all of the conditions, the output is going to be a high impedance line. Okay, so that's a mux which is implemented using a if statement. Now, is there a more compact way of doing this because there are multiple branchings? Yes, and we can use a case statement. Now, I want to mark this. Okay, in case statement is just like if statement. If certain condition is true, then it's going to do a bunch of statements. But unlike if, it is going to check the remaining conditions also. So if case one condition is true, then it is going to execute something. Then it's going to check the next condition. If it's true, it's going to do whatever it says. So there can be multiple conditions which may be true, and it will do what it's supposed to do, right? And here you cannot have a break statement like in high level languages. You cannot put an exit, okay, because exit is specifically used, or next is specifically used to with the loops. They are not used with the branching. Okay, so this you have to keep in mind. So you cannot have a exit statement as a part of statements in a conditional case statement, right? So let's do a case statement. Okay, so we'll take the same mux example and turn it into a case statement. So let's see if I'm recording. Yeah. Okay. Okay, so once you are done with this verification, you can just go to simulate, and then you can say, come on, you say and simulation. This will close the simulation. Okay, so now same thing I'm going to do with the case statement. Okay, so I'm going to say right click and say add a new file, and I'm going to say here use process 1, and say okay, and this is an empty file. Okay, so that's an empty file. So what I'm going to do is I'm just going to copy the entire thing there. Control C, Control V. Okay, and I'm going to change this to use process 1, and end of use process 1, UP1 of use process 1 is end use process 1. So now I have turned it into a new entity which is called use process 1. So here I am going to do slight variations in here. So this if statement I'll throw out, and I would say variable. Okay, and that is called select, and that's a std logic vector, which is a 2-bit vector, which is going to be 1 down to 0. Okay, so this is called a variable declaration, and variable declaration can take place in the declaration section of the process and declaration section of functions and procedures. So we'll come to functions and procedures later. Okay, so now having done that, first thing I can do here is I can say select, okay, is assigned. So this is assigned, and then aggregation s1 comma s0. End of the story here. Okay, so we have a select. So now I can write a case statement. Case select is, okay, and then I would say end case. So whatever I write, it will be inside this case statement. Okay, here I can say when this value is 0 0. Okay, when it takes this value, q is assigned I0. Okay, then I can put the next condition when 0 1. So under this condition, q is assigned I1, and then I can say when. So let me check if I'm recording. Yes, I'm recording. So then I can say when this condition sorry, when this condition, then Q is assigned I2, right? And when the condition 1 1, then Q is assigned I3. So it's the same thing, but then I am going to add, like in the case of if there is else, for all other conditions, then I can say when others, then Q is assigned others, and then a concatenation of Z. Okay, so this is going to be a case statement. That's how you write a case statement. Let's see if there is any error. So I'm just going to compile it. Okay, so there are 6 errors. I have to figure out what has happened here. So let's see. Down to spelling mistake. DOWN. What? Line number 13, 15, 13, 15. Oh, down to. Just keep note that this is brown colored, so you will not make mistake. Let's compile this again. Okay, so this time it's successful. This was this down to which was giving a problem. So now if you want, you can verify this again. So you have compiled it. You can say start simulation. You can go to my test library. You can choose out your entity, and it's going to go to line number 12 and stop there. Okay, again I need S1 S, come on. Okay, so I need I0 to S0 S1, sorry, I0 I1 I2 I3 S1, this and Q, and add to wave. And here I'm going to give them default values: 2A, 2B, 2C, two D, and then you are going to have 0 0 0 0, and hence the output is going to be 2A. So I'm going to simulate this, so the output is 2A. Then I can make this one as 1 and simulate this again, 2B. Then I'm going to make this one as 1, that's going to be 2D, right? And then I'm going to make this one 0, that's going to be 2C. And if I leave one of them to be unknown, force a constant U, and then do it, it will be high impedance. This is high impedance, right? So this has same functionality as with the if statement. Okay, so I am going to close this one. Okay, so now sorry about this. Okay, so now you have seen two things. one is the case statement, other one is the if statement. Now I'm going to show you a for loop. Okay, then the idea is to convert an integer into a binary number, right? So I'm going to write a code for that. So I'm going to say new file, so add to project, new file, and then this one I'll call use process 2. Okay, and in this use process 2 I can write there the usual stuff, library IEEE, use IEEE dot std underscore logic underscore 1164 dot all. Once you're done with that, you can say here entity use process 2. I think it's 2, right? Yes, use process 2 is and use process 2. Okay, so having done that, I am going to say here port, and here I'm going to write the port information. So I want to receive an integer, so let's call this as n, and I'm going to receive n as an integer, right? And this is of the mode in, right? And the next input is going to be output is going to be q out, and this is going to be std logic vector 7 down to 0. Okay, so this is how you write an entity. Then you're going to say architecture up2 of use process 2 is, and then you are going to have a begin for this architecture, and then you are going to have an end and up2. Okay, so this is how you're going to write the basic structure. Now I want to show you how to convert this into, like, how to do the conversion. So I can say a process, and process is sensitive to n, right? And then it is going to have a begin of its own, and then it's going to have an end of its own. Okay, so now there is this section which is called the declaration section, where I'm going to declare a variable and call it vary, is again an integer, right? And then I'm going to create a variable that is res, and that has std underscore logic underscore vector. Then this one I am going to do 7 down to 0. Let's see if this is correct. Okay, now I have to do something to convert this, right? So first of all, what I'm going to do is I'm going to say my variable vary is assigned n, and my variable res is assigned well, you could have said that, or you could also say others, all values 0, and the end of this. So these are the initial values. Then I'm going to do one thing. I'm going to say for I in 0 to 7 loop. Okay, so that's how you write the for statement. If you see here, okay, loop, and then you are going to have an AND loop. Okay, so that's done. Okay, so what's inside the loop? Inside the loop, I'm going to say if vary mod 2 is equal to 0, right? So I am doing a vary mod 2. Vary mod 2 is equal to 0. Okay, then I'm going to say res I is, so res basically is a variable, right? So you have to use this assign. Res I is assigned 0, else res I is assigned 1. So if it is divisible by 2, I am going to assign a 0, else I'm going to assign a 1, and then I'm going to say and if. Okay, once I'm done with this, I am going to say vary is equal to vary divided by 2, correct? And when I come out of the loop, right, I am going to say q is assigned res. Okay, so let's look at that. Right. Okay, so let's see if compile succeeds. Okay, there is one error. It says empty source file. Empty source file. Let's check this. Process variable begin res is assigned use process 2 up of use process 2. Okay, let me put you on hold to figure out what happened here. It says failed because of one error. Empty source file. Oh, is it not saved? Save. And then I am going to say compile. Now we have two errors. Okay, so the error is assignment near this on line number 22, and 15 is not a signal. On line number 15, okay, this is not a signal. Okay, and 22 there has to be a assignment. Okay, so this is done. So now I'm going to save it, and I am going to compile this again. So now this time it's successful, so this holds true. Let's see if it logic is correct. So I am going to go to simulate and say start simulation, and here I'm going to go to my test and use process 2, and is going to stop at line number 12, line number 10, sorry. Okay, so it stops at line number 10. Is waiting for a signal. Where is it? Not this one, not this one, over here, line number 10. Okay, so here I'm going to add these two to the wave, and here I am going to specify everything as a hex, but I want to display it as a decimal. So decimal. So if I put here 25, so hex 25 is equivalent to 32 plus 5, 37. Okay, and let's run this. Okay, so basically integer 37 is equal to hex 25. So that's what it did, right? So this is what we expected, right? It is going to give you a hex number. If I give an integer 37, it is going to give you a hex number 25. Okay, so this is true. Now, if I exceed 7 bits, is it going to cry? So if I go here and say force constant, and let's say that this is going to be 120. This is a hex 120, which is 16 raised to 2. Okay, plus 256 plus 16. So let's do that. Oh, okay, wait. Force 25. How's that? It's going to cry. Okay, 125 is 293. 255. Okay, 125 is 256 plus 32. 66, 76, 86. 125 hex I gave. CALC. I gave in hex as 125. That is 293 as the decimal. Correct? It should give me back the hex. But you will see something strange will happen. Okay, it gave you 25. Okay, so basically it is giving you an absurd number. Why is giving you an absurd number? Because you have exceeded 7 bits. And this is a runtime error, and there was no indication of runtime error. Right? So you understand that when you write something, you have to be careful. It will not take care of your runtime errors. Okay, so I'm going to end this here. End simulation. Okay, so I can convert an integer into a hex number by this algorithm. Now the question comes is, can I do this with a while loop? Okay, so I have demonstrated for loop. So let's see what I have covered. I have covered a for loop. So let's change this to, okay, covered a for loop. I have covered if and case statements. Okay, so I have covered if and case statements. Right. And now I have already shown you what is a process. Right. So I am going to show you now a while loop. Do the same thing using a while loop, right? Okay, so let's do that. While loop, and yeah, exit and next. Okay, let's do that. Okay, so I'm going to go here and say add to project, a new file, and I'm going to call this as use process 3. Okay, use process 3. Okay, and this is going to be an empty file, and I am going to go and copy whatever is there in process 2 in process 3 file, and I want to show you a while loop. So control V. So everything is fine. This is entity is process 3. architecture is UP3 of process 3 and end of UP3. Okay, so now here I am going to get rid of this for loop. Okay, I need to do the same thing with the I loop, but I still need a indexing. So I would say vary comma I, right? And here I can say I is assigned 0 to start with, and then I can say while, okay, condition vary is greater than 0 and condition I is less than 8. Okay, loop, and then you can say end loop, correct? So we are done with that. So what am I going to do? I'm going to say the same statement if, okay, so the same statement will be there. So I'll go to the previous one and say if, else if, and this. Okay, so I'm going to just copy this. These are going to be repeated. Okay, if okay, so this I'm doing. I has to be updated. So I'm going to say I is equal to I plus 1. Correct? So essentially I'm doing the same thing, but instead of a fixed count of for loop, I'm basing it on a condition that the number which I'm consecutively dividing by 2 stays greater than 0. So I have to run that loop that time, or I run out of a condition where I has exceeded is okay, and by I has exceeded 8 or exceeded 7. Okay, so let's see if this compiles. Okay, always a error, empty because you haven't saved it. Okay, once you have saved it, then run it again. Okay, so it is successful. So it means that this is compiling properly. Now let's see if the functionality is fine. So I'm going to say add it, start simulation. I'm going to go to my test, and here I'm going to go to process 3. Okay, then I'm going to say add to wave, and here I am going to say radix is decimal. Okay, and I am still going to enter a hex, which is 25 equivalent to a decimal of 37. I should get back 25, and I get back 25. So functionality wise it has remained the same as the for loop, right? The while loop has remained the same as the for loop. It's just that it is a different way of implementing. Now here I want to do one thing. Let's give here 258. So force a constant, and I'm going to call this as a 258, correct, and say run. So now if you give 258, you see here you have got 600. So 258 is equivalent to 600. So if I go to calculator, okay, 258 in hex, in hex 258 is equivalent to 600. But then it is showing me 58. So how's that? So if I minus from this 256, so I have once run out of the loop, and again, so 600 minus, cancel. So I have a 600 integer, and so I'm going to do a decimal here. So I have a 600 as a decimal, and I have run out of it. Sorry, go to a regular calculator. Okay, so I have 600 and I have run out of it 256 twice. So I am left with 88. Why does it say 58? Ah. Okay, 58 is decimal. Let's look at hex. What is 58? 88. Go to programming and you are going to enter decimal 58. No, sorry, hex 58. Clear. You are going to enter hex 58, which is going to be decimal 88. So basically, it's displaying a hex number here, 58, which is equivalent to 88. So what it's saying is that 7 bits are going to overflow twice, and what you will be left with is going to be a decimal 88 or hex 58. So you are going to get a hex 58. So algorithm is still right? It's just that you have fixed your bits to 8 bits, and that's why it's overflowing twice and giving you the remainder as 88 decimal or 58 hex. Okay, so I guess you understood that runtime errors cannot be caught at the compile time, right? So end simulation. Okay, so we have demonstrated a while loop. Okay, so we have demonstrated a while loop. Okay, so now let's say I'm just going to make a copy of this. I'm going to say, okay, I want to demonstrate exit. Okay, so let's say I have this removed. Then if I less than 8, lie less than 8 has to be removed. Then it is going to give you a compile error, because it's going, if the number is greater than, so if the number is greater than 255, then the loop is going to run for more than 7 times, and this index would be out of range. So you cannot protect that, right? So what can I do? So I am going to say add new file, and then I'm going to call this as use process 4. Okay, so this is going to be empty file. I'm going to copy as is the contents of use process 3, control C and control V. Okay, so only thing is I'm going to make this as use process 4, use process 4, up4 of use process 4 is going to be up4. Okay, now everything looks okay. Let's say I got rid of this condition. Okay, so this is going to loop beyond 7 bits, and this is going to run into error. Okay, so what I can do is I can say here, if, okay, condition I, okay, so I can put here condition I is greater than 7. Okay, then I want to exit the loop, right? And everything else is optional actually. So this is going to work. Else, well, this is optional. You need not enter it. So this is good enough. This is going to do the job. Okay. So let's go here and save it and then compile this. 2 errors again. What happened? If, okay, and if I forgot, sorry. Okay. So, and if, okay, fine, all set. Save and say compile selected, so it's successful. So it's going to work the same. It's just that I have removed that condition out of the while condition, less than 8, right? But I have introduced it over here. So now this is not going to give me an error. So if I was to start simulation, go to my test, go to process 4, say OK. So I'm going to select these two signals, add it to the wave file, and here I am going to do a radix, display this as a decimal, but entry is always a hex. So if I do a 25 and I say run, so 37 is equivalent to hex 25. So 25 is the output, fine. Now if I say force this to 258, that is equivalent to 600, and run this, so the answer is hex 58 or decimal 88, which is the same as the previous one, right? So what different has happened here? I'm going to say end simulation. Okay, I have constrained my output to be 8 bits by earlier by using an AND here, right, in process 3, while in process 4 I didn't use AND in my while loop, but I used the exit. So that exited this while loop as soon as I exceeded 7, right? And there is an optional I can do else. So basically else I can say next. So this is all cosmetic. Next is not going to do anything, but usually the next is there if this was not a last statement, if it was earlier, right? So if I, so for example, if this statement instead of being here, okay, was being here, okay, so this is going to be functional same way. It's just that it's going to check in the beginning if I is greater than 7. If it is greater than 7, it is going to exit the loop and Q is going to be assigned res. If not, okay, if I is less than 7, then next. So basically this is going to do a skip everything here. So it is going to skip everything and the answer is going to be 0 0. So it's not going to be the logic what we want, right? So it is a wrong place to be. So what does the next do? What next does is it's going to ignore all the statements after that in the loop and start fresh on the loop again here. So what is going to happen in this situation is if I is not incremented because it is outside, so even variable is not divided, right? Variable is not divided, so this is going to be a never ending loop, right? So this is a wrong place to be. So you are going to check it after the I is incremented. Okay, and this next is optional. It is not going to do anything, though next means that skip the other lines and go to the next iteration of while loop. That's all it means. So if I want, I can just run, compile this first, okay, and run it just to show that next is doing nothing, but next basically means that go to the next iteration of while loop. So I'm going to say start simulation, and I'm going to go to use process 4, and it'll just come up. I am going to add to the wave, and here I am going to display this decimal, but enter it as a hex as 25, which is equivalent to 37, and it will give back 25. That it does. And when you exceed it, when you make this as 258, it will be equivalent to a 600, overflow twice and give me 58 hex. It's doing the same thing, but what I have shown you is what is exit and what is next. Next, I want to see an assert state. Okay, so what is assert? It says assert a condition is false, then report something. Okay, so I can do it like this. So let's go ahead and close this and simulation. Okay, let's say I want to check. Of course there is a break here. Okay, of course, if I is, so for example we were at process 5, so here if I exceeds 8 7, if I exceed 7, this is going to exit, right? Now it is exiting, but it's not telling what has happened, right? It's not asserting anything what really happened. Okay, so I can do the following. Okay, before assert, before this exit, I am going to say okay, I am going to say assert condition. Okay, uh, I sorry assert I is less than 7, so it's not going to do anything for I less than 7, but this has to be out of the loop, not in this loop, because I want to show you what assert means. So I can show here assert condition I is less than 7. So this condition is true as long as I is less than 7. So it is assert statement is going to do nothing. But as soon as I becomes more than 7, right? Next is 8, right? If I becomes 8, then I want to report input exceeds 255, right? And then I will say severity as warning. Okay, warning is a keyword. Okay, so now if I do this, as soon as I becomes 8, it is going to inform me that input exceeds 255. That's a warning. And then when it checks if I is greater than 7, it is going to exit the for loop. So assert is just some form of a testing, right? So let's go here, and so we did it in 4 itself, right? So let's just save it. Let's run this again. Okay, go to compile this first. Compile. Okay, what happened? Successful. Okay, I'm going to say run start simulation, and here I'm going to go to my test, and this I'm going to run. Okay, so this is going to check the runtime errors. Say add wave. So this is can be used in assertion based testing. Again, the radix I want to display is decimal, though I'm going to enter a hex here, which is let's say 25, and it's going to give me back hex 25. decimal equivalent is 37. I run it. So he says run in the window, transcript window, you say run, and the output is 37 means hex 25. Now if I make this 258, then this is going to be 600, right? Okay, so if I run this, it says it is 600, remainder is hex 58, but look here, it says input exceeds 255, right? Input exceeds 255. So that's what it has done, right? So this is what an assertion has done. It's a warning. Now, if I do an AND simulation here, and I want to do this testing even before I go and run this, I want to do testing somewhere else. So here, let's close all others. Here, the assert was used here to issue that warning. Okay, so I'm going to remove that assert from here. I want to check it prior. And where can I check it? I can check it inside the entity itself. So what you are seeing over here, this is the declaration section of entity. I can have a begin here. Okay, and here I can do a process. Assert being a sequential statement, it cannot be outside the process, and bodies usually have concurrent statements, so I cannot put directly assert here. So I have to do a process n, right, and then I have to say begin, and then I have to say end process. So you are seeing that I'm writing a process in the body of an entity. That is called a passive process. And in a passive process, you cannot do any assignments. You can only assert something, right? So here I can say Control V. So I'm going to assert here itself that in this case, I am not going to check this. I'm going to check n is greater than 255. Okay, so instead of asserting, doing an assert inside this, I am doing inside the entity itself. So as soon as somebody enters n greater than 255, it's going to assert this. And the thing is, if I put here an error, then it will not run. It will just exit. So let's see how it behaves. So I'm just going to say save. And here I am going to say compile. So I did compile all, but anyways, so this got compiled. Okay, fine. Okay, so now let's run it. Start simulation. Go to test, my test. Let's see if I'm recording. Okay, so here I'm going to run this 4, but now the assertion is coming from somewhere else, so you will just see it. It is coming from a passive process, which is inside the body of an entity. This body of entities is optional. Okay, usually in books you don't see that, but it's used mainly for assertion based testing. So if I'm going to show you severity of error, okay, earlier it was warning. So if this was, okay, first of all I'm going to change the radix to decimal, so it's going to display a decimal, and I'm going to force a hex, which is 25. Okay, and I'm going to run this. So 37 returns me a hex 25. Okay, what happened here? Oh, I may be wrong. So now I will not be able to enter anything. Okay, wait. Let me see what happened here. And simulation. Okay, what happened? While the assert is less than 255, so it is true, don't report anything. If it exceeds, then report. So again I was doing a mistake. So assert means if this condition is false, it's not going to do anything. If this condition turns true, then it's going to do that. So let's compile this again. So in that case, severity error, it should have come out. It should not proceed. But let's see this simulate. Let's compile this first. It is compiled. Okay, then simulate, start simulation, and go to my test, use process 4. Now I'm going to add these two. Sorry about that. Add to wave. I'm going to change the radix to decimal. Put a hex number here. 25 hex. It's going to return me a hex. Why is it issuing an error here? Input exceeds 2. Where is it coming from? Okay, let me put you on a hold for a second. Okay, so I figured out what happened. I didn't save last time, so now this is correct. So if n is less than 255, it's not going to report anything because it is true. When it turns false, then only this assertion will take place. So I will go here and say start simulation. I'll go to my test and go to process 4, and here I'm going to give it something within the range of 255 and see what happens. Come on. Okay, so I am going to add this to the wave, and here I am going to change radix to decimal, put in a hex number of 25, and when I say run, it returns me 25. But notice here in transcript there is no warning here. Now let's say if I exceed this, force 258, and here I run this again, so you see warning, input exceeds 255. Okay, so now when it exceeds 255, it is asserting something, right? Asserting that this is greater than 255. Now if I go back to, let's say, 58, which is less than 255, and if I say run, so there is no issue of that warning, right? So you have seen here that I have used a passive process inside an entity. And what's the nature of the passive process? You cannot do any signal assignment inside a passive process. You can use variables, you can do a type declaration inside the declaration section of passive, but in this passive process there cannot be any assignments. So that's why it is called a passive process. And passive process is usually in the body of an entity, and body of an entity is optional. Okay, it doesn't mean that the entity cannot have a body. Usually you see in the books that entities doesn't have a body, but VHDL allows you for assertion based testing. Usually for timing analysis you can use assertion here, okay, to see if something exceeds the timing, and then you can give out a warning that something has exceeded the timing on a certain signal. So that is used in assertion based testing. Okay, so now here I am going to stop. Okay, so what we have learned is all these constructs. Okay, one more thing which is remaining, which I just want to complete. Okay, so let's say this is covered. Okay, process need not have a sensitivity list. So in that case, I can test this over here. So instead of this, I can remove it from here, and I can say just before the process ends, okay, I can say wait on the signal, which is n, or a list of signal comma separated. So it's going to behave the same way. So let's see if it behaves the same way. So here I am first going to save this, then I'm going to compile this, and then I'm going to run this. The compilation is successful. Then I'm going to run this simulation, go to test, go to use process 4, and go here and add this to the wave. Just 1 second. So now the same process is working without a sensitivity list, but it is going to wait on n before the process ends. So it's going to always, just what the sensitivity list was doing, I used the wait statement. Similarly, you can use wait for or wait until, right? Usually used in testing a lot. Okay, so I'm going to give it a radix of decimal, and I'm going to give it a hex number, which is 25, which gives a decimal of 37, and run it. It gives you 25 back again, right? So it's working the same way. So what I'm saying is that this wait statement can do that. Now, the reason I'm using a different tool is that these are all more or less related to verification or testing, and I don't want to show this, and probably Vivado won't work in some cases because Vivado allows a certain subset of VHDL which is synthesizable. Something which is not synthesizable, like for example assertion and all that, you can put there, but some things like which are not synthesizable with a for loop or a while loop, okay, so that will not be allowed in Vivado. So I used a QuestaSim to do that. Okay, so I have covered sequential statements and process in detail. Okay, so I'm going to stop here. Thanks a lot.